We're now going to talk about Lebesgue-spaces and Sobolev spaces. These spaces are named by the famous French mathematician Henri Lebesgue and Sergei Sobolev. Let's consider a subset of Rn. In this illustration we have chosen n equal to 2, so it's in the plane. And we assume that this subset is an open bounded domain. Bounded means that it's possible for us to find a circle which surrounds this region omega. The boundary of omega is called del omega. Now we define what we mean by Lebesgue space. We call it L2 of omega. Omega is referring to this subset omega. And this space contains all functions, call them V, with the property that the integral over the square of V is less than infinity. So what does this integral mean? This is some abbreviation. With this symbol, this means that in our case, where omega was a part of R2, generally in Rn, it means this double integral of f of x1, x2, dx1, dx2. So in this case, we have the x in this direction is called x1 and x2 in this direction. Normally you are used to calling this x1 direction for x and x2 direction for y, but when we are using more than two variables, we usually need this kind of indexations. So what does this integral mean? Well, if we, for example, if we have some square like this, and we want to take the integral over this square, then it's very trivial to do this. We start with, for example, let's do it like this. A, B, we can say C, D here, and the integral over omega of f of x dx is then in this case the double integral from A to B in the x1 direction, and from C to D in the x2 direction. So here we have f of x1, x2, dx1, dx2. And note that x is just a vector in R2, so it consists of these two coordinates, x1, x2. Of course, we can do this in several dimensions and as well, and this abbreviation is used for simplicity only. So note that it's more complicated when we have we don't have a rectangle like this, but those who have studied vector analysis and integral theory with several variables, which you should have, can recall how to understand the integral in such situations as well. Now let's go back to the definition of this space L2. We can write this in a more mathematical way than writing it like this. So mathematicians are often using symbols like this. This means the set of all functions v with the property. This symbol means with the property that the integral over the square of v dx over omega is less than infinity. Then we have a more advanced type of function spaces called, this is the Lebesgue space. This is the so-called Sobolev space, W12 of omega. It's a set of all functions v with the property that v belongs to L2 of omega, and all partial derivatives of v, first order partial derivatives of v, belongs to L2 of omega. So this symbol 1 means that the first derivatives belongs to L2. Let y, capital Y, be a subset of Rn, which is a cell in Rn. That means in R2, for example, that it's a rectangle, the interior of some rectangle. Then the space, this is also a Sobolev space, but the space V per 1, 2 of capital Y is equal to the space of functions V belonging to the Sobolev space W 1, 2 of Y, with the property that V is Y periodic. And what does that mean? If we have this rectangle here, this rectangle, the interior of the rectangle capital Y, and in order to be a function which is periodic, it means that the function is have the same values on opposite traces of this this cell Y. So here and here the functions are equal. Here and here the functions are equal. And here the functions are equal. This may seem a little bit difficult for you to grasp in the start, but when you are considering examples afterwards, this will be much easier to understand. So don't worry about it. The function W0 of 1, 2 of omega, that's just the space W1, 2 of omega with the property that u is equal to 0 on the boundary of omega. So in this case, omega does not need to be a rectangle. But in the case when omega is a rectangle, let's call it capital Y, then it's possible to see, it's rather easy to see that W0 of 1, 2 of capital Y is a subset of the space of periodic functions W per of Y, and that this space is a subset of the larger space W1, 2. And the largest of these spaces is in fact L2 of omega. Moreover, if omega is any arbitrary domain in Rn, it's also easy to see that W0 of 1, 2 of omega is a subset of W1, 2 with no 0 on the boundary. And this is, of course, a subset of L2 of omega. So these spaces are vector spaces. All these. In fact, they are Hilbert spaces. And let's now explain how these spaces are constructed. What is scalar product? The scalar product, call it R in L2, is defined in the following way. If you have a function u and you take the scalar product with the other function, then this function with this value will be equal to the integral of u times v over this region omega. Moreover, as usual, the norm of a vector is just the square root of u, the scalar product of u with itself. So in this case, using this definition of the scalar product, we see that the norm is equal to this square root of this integral. The scalar products in all these Sobolev spaces, when omega is equal to y, it's when omega is a square in or a rectangle in R2, a cell in Rn, then this makes sense. But all these spaces, in any case, have the following scalar product. We have the same scalar product as in L2, but we add the following. We take the gradient of the function u and multiply it with using the standard scalar product in Rn with the gradient of v, and taking the integral over omega of this function. And recall that the gradient of a function u is defined in the following way. It's the partial derivative of u with respect to the first variable. That's the first coordinate of this vector. The partial derivative of u with respect to the second variable x2, and so on. Note that the norm of u in the Sobolev space is defined as usual as the square root of this scalar product, which is due to the definition of the scalar product in this Sobolev space. We have this definition of the norm in these Sobolev spaces. Note that the square of the absolute value of the gradient is just the gradient of u, the scalar product of the gradient of u with itself, and by taking this scalar product, you have this vector. You find that it's these squares, the sum of these squares.